Hi, I'm Ezra,
I'm Sam.
I'm Isabella.
And I'm Stanley.
and this is our SmolVLA hardware acceleration of the vision encoder specifically.
To give a quick overview on the project we're doing today, we are accelerating the SmolVLM model, which is a component of the SmolVLA model. It combines three transformer architectures, a vision encoder, a text encoder, and an action expert that produce action chunks. The vision encoder is our focus today, which while having a smaller parameter count, has a token length of over 8 times the other two transformers.
The vision encoder is broken up into two parts, the attention and the multi-layer perceptron. Sam and I focused on attention, while Isabella and Stanley focused on the multi-layer perceptron. So why did we choose to accelerate a small VLA model in the first place? VLMs are computationally expensive and memory heavy. Running them on edge robots requires low latencies and high energy efficiencies. For example, a drone, you can't just strap on a GPU, which can take sometimes hundreds of watts. And if you need that same level of compute, an FPGA can now take this and do the same workload, potentially at much greater efficiency.
In this project, we use Allo, which is the accelerator design language developed here in the Cornell Zhang Research Group. Allo allows us to write our HLS kernels in Python using a NumPy-like syntax. This is in contrast to the C++ language used by HLS languages like Vitis. Allo allows us to easily switch the data types we are using, giving us massive flexibility. In addition, we can target different devices, ranging from AMD FPGAs to AI accelerator cores found in AMD CPUs. Allo also allows us to verify functionality against known PyTorch implementations, which makes testing much easier. Allo separates the functionality of a kernel with the scheduler. This means that to implement a kernel, we first define how the kernel processes data, then we use the customize function to change how it maps to HLS code. This is in contrast to something like Vitis, where in order to apply optimization like loop reordering, we would have to modify the functionality of a kernel. This means that Allo allows for structured architectural exploration more easily, since we only have to modify the scheduler function, not each kernel every single time. Allo also supports custom kernel composition. This enables scalable design, which will help make our life easier when implementing a larger HLS design.
So when approaching accelerating this model, one of the techniques that we used was roofline modeling. We used roofline analysis to determine the expected OI and throughput for the three transformers. The results showed that for each of the transformers, they were compute bound and not memory bound. The model that we used suggested that in order to achieve a 10 Hertz throughput rate, we would need a throughput of 2 teraops for the vision encoder, as it has the largest number of input tokens.
One of the most powerful techniques we used was actually inspired by a paper written by Professor Zhang and his research group called Understanding the Potential of FPGA-Based Spatial Acceleration for Large Language Inference. And in that paper, they discussed the benefit of using spatial architectures, where instead of having a temporal architecture where every function kind of does very parallelized and fast processes, writes the data back to memory, and then reads it again, we create this data flow, right, where every single independent kernel is laid out in a kind of spatial format, hence the name, and then is streamed via FIFOs. This seriously reduces memory accesses and allows for immense speed up.
Normally, GEMs and other algorithms are normally implemented with a triple nested loop, and we optimize typically through unrolled pipeline pragmas. However, for some of our matrix multipliers, we use a systolic array where data is streamed in from each dimension of the systolic array into the processing elements. This means that data only moves locally between PEs, so lots of memory traffic is eliminated, allowing us to be more efficient.
Another one of the techniques we used was quantization, which is basically mapping a wide range of input values to a smaller finite set of output values. For instance, we quantized our weights down to a 1-bit format from FP32. Having a smaller set of output values means we have fewer bits per parameter. This means we can have more parameters, increasing effective memory bandwidth. Smaller parameters also decreases computational intensity, allowing for faster computations. Although precision decreases slightly with lower bit formats, this is generally worth the increase in performance.
So what does multi-headed attention actually do? So it starts by computing these query key and value matrices from the input matrix X. Then, Once it has these matrices, it does a QK transpose matrix multiply. This represents how much attention each token should get. Then that is passed into a softmax function, which basically turns this attention into a calculated weighted sum. The output of this is then matrix multiplied with a value matrix, and this applies the values of tokens by their weighted attention. This is now finally passed through another matrix multiply, which takes this from like a single-headed low-dimensional space to the full d-dimensional space. And then finally, this goes through a layer normalization, which normalizes all the weights before being added back to the initial input x as a delta. Taking inspiration of this spatial architecture and applying a data flow to it, we basically created the data to move to the next step as fast as possible. And what this means effectively is, say, in order to produce one row to feed into the softmax, we need the entire K matrix to be outputted as fast as possible, but only one row of the Q matrix. So we made sure to pipeline accordingly to achieve this. Then once we have a singular full row in the softmax, we're then able to pass that on, get the maximum value, normalize it, and then continue it down all the way to the V matrix multiply. But then we took this further by applying a data flow. And what this does is, while one thing is doing the matrix multiply with the V and the softmax is now computing the next row. This effectively pipelines the whole thing and creates a much more efficient interkernel fusion.
We designed each loop in our kernel to reach an II of 1 for all of the loops in the data flow, with the one exception of our softmax sum loop, which reaches an II of 4 because of a read after write memory dependency between the heads. To resolve this, we split the sum into 4 independent buckets, each of which can run in parallel, which, while still achieving an II of 4, requires a quarter the number of total cycles, maintaining the maximum allowed time in the data flow. We also pipeline and unroll the per head loop by 4 in order to better navigate pipeline dependencies, as each head was completely independent of each other. While this required more hardware, this sped up the runtime of our kernel. As a result of these optimizations, we were able to achieve a time of 30 milliseconds for a single layer of attention, which is equivalent to 266 gigaops per second. And this was done with quite low hardware utilization, such as a 4% on our DSP and 10% LUT usage, which indicates that there's a chance that we could increase our throughput by increasing the amount of hardware used. Because of the lack of a HBM control interface in Allo, it was not possible for us to calculate an effective OI usage. Compared to the baseline implementation that we made, we achieved over a 150 times speedup, indicating that our optimizations were indeed effective at increasing throughput.
The other part we implemented was the MLP. MLPs are feed-forward networks that use the context provided by the attention layers to process information about each token. For the MLP found in the SmolVLA, they consist of 2 feed-forward networks, which expand the features to a higher dimension. Then there's the GLU layer, which introduces nonlinearity. This allows our model to capture nonlinear features, which is extremely useful. Finally, there's the layer and norm layer.
For the MLP, we use the GLU activation function, shown on the right, because it provides a smooth, continuous derivative, which helps optimization during training. GLU is mathematically expensive to compute, making it difficult to implement efficiently on hardware. In practice, approximate versions of GLU are often used because they are much cheaper to compute and still provide performance that's good enough for most applications. For instance, while the full GLU function is useful for training, inference does not require the fully accurate function, allowing for us to benefit from using these approximations. As mentioned previously, computing the exact GLU functions requires evaluating transcendental functions such as the error function, or ERF, which is computationally expensive. To reduce overhead, simpler analytical approximations can be substituted for the true GLU function, while maintaining very similar behavior as seen in these examples. The one on the left is more expensive to compute, but is more accurate compared to the one on the right, which is faster to compute, but less accurate. Since these approximations closely match the original curve, we can perform faster computation with only a small loss in accuracy.
Analyzing the computational work distribution in MLP, we can see that the 2 fully connected layers, who are represented by matrix multiplies, their flops represent over 99.6% of all flops in MLP. This is due to the extremely large tensor shapes involved with these calculations, in contrast to the smaller matrix multiplies in the attention block. The next largest block, which would be the GLU layer, represents less than 0.4% of all floating point operations, and the bias operations and the quantization operations are just blips on the breakdown in the distribution. Our baseline MLP kernel computes all the operations in around 8 seconds. After applying our optimizations, including the 8x16 systolic array, we were able to have a 108x speedup, reducing our execution time to only 0.075 seconds. The reason why our systolic array is comparatively so small is that Allo struggled with synthesizing larger systolic arrays. There is potentially more speedup available by synthesizing a larger systolic array, although this would significantly increase compilation time.
In conclusion, we were able to successfully model an attention layer that was in the SmolVLA vision model using Allo, and we verified it using the PyTorch functional level tests. Through this, we not only learned a lot about Allo, but about attention networks in general, deepening our insight in these areas. We also tested various systolic array architectures for our MLP and achieved about a 100x speedup.
Some of the future work, however, includes a goal we tried to hit was this 10 Hertz vision encoder. Unfortunately, due to limited memory streaming and setting up the systolic array within the attention network, we were not able to hit that target throughput. Additionally, we actually found lower bit quantization, such as 4, 2, and 1 bit quantization. However, I doubt 1 bit quantization is recommended for our case. That actually has already been pre-trained and could be loaded immediately. And lastly, I think to fully build a proper data flow and spatial architecture, you need to heavily integrate this high bandwidth memory streaming